This presentation is about the pressure-temperature relationship and then a way of combining all of my gas laws into one, or at least the three major ones: Boyle's law, Charles's law, and then Gay-Lussac's law. Okay, so we call this Gay-Lussac's law, or at least our textbook does. Some books will call this Amonton's law. There is some speculation that Gay-Lussac actually had nothing to say about the pressure-temperature relationship, but Mr. Amonton did. But you know, that's one of these debates that goes on in chemistry, and I don't lose sleep over it. So anyways, whenever I think of Gay-Lussac's law, I think of my kind of mischievous younger days, in the days before cell phone cameras, so no one was taking pictures to have any evidence, so I'm going to swear that you never heard this from me, but I was a child that couldn't take a warning label at face value, so I noticed that on many aerosol cans it said not to expose the aerosol can to heat or flames, so I had to investigate exactly what was happening there. So me and a few of my friends started a small bonfire and tossed aerosol cans into the bonfire, and let's say that quite a bit of excitement ensued after that. Let's just say that the cans exceeded the pressure limits of the container, and there was a loud sound that followed when the container was breached. So basically, there was several explosions that went off. We'd probably been arrested as domestic terrorists in this day and age. Anyways, so as I increase the temperature, I increase the pressure in the container. So I've got another direct relationship going on. So the pressure is directly proportional to the temperature, and I again can move that T over to the other side. So the ratio of pressure to temperature is going to give me a constant, and so long as I'm working with a fixed system here, my pressure-temperature relationship should remain constant for my gas. So this is the basics of what our book will refer to as Gay-Lussac's law, the pressure-temperature relationship. So I can put this to work here. I've got a problem here where a diver was taking a look at the pressure in a spare tank of compressed gas that they were using, and saw that it was 150 psi on the surface, and then when it was down on where they were diving, it had decreased in pressure. So the reason the pressure decreased is the gas particles started moving slower. They were hitting the container with a little less force, and as such that exerted less pressure. So the pressure was actually going down in the container, and that makes sense. That's what we decided. The pressure and temperature move in the same direction for Gay-Lussac's laws. So let's tabulate the data. P1 is 150 psi, P2 is 144 psi, and T1 is a grand 303 Kelvin. So I want to figure out what the temperature is. So again, I'm going to use the law that's given, so don't worry about this. All of these laws are going to be tabulated on the useful information page of the next unit exam. So again, I purposely put the unknown in my denominator, and as I mentioned, cross-multiplying is one way to get at that quantity, so I'm going to stick with that. So when I do that, I get 303 Kelvin times 144 psi. Pressure isn't one of these units that is really sticky. As long as I'm keeping in the same unit family here, I don't have to worry. So psi to psi is going to be just fine. Okay, so I need to get T2 all by itself, so I'm going to divide by 150 psi on both sides and cancel accordingly. And what I got for my calculation was 291 Kelvin. And I was a little curious what that was in terms of the Celsius temperature. And when I subtracted 273 from 291, I got 18 degrees Celsius. So the temperature where they were diving was, pretty reasonable, right around room temperature, maybe a little bit cooler than room temperature, but nothing terrible. Okay, occasionally we'll run into a problem where we've got pressure, volume, and temperature all changing at the same time. So in order to handle this, we use what's called the combined gas law. The combined gas law. Been in Iowa too long here, the word combine, I say it the wrong way. So if you look at this closely, squint hard at this one, and ignore the T2s in the bottom, you can see the basics of Boyle's law. If I cover up the V's, I see that I've got Gay-Lussac's law, and then if I cover up the P's, I've got Charles's law. And it works out that the ratio of pressure times volume over temperature is going to be a constant for gases. So I can make use of that. So I've got 1 liter of gas, and I'm collecting it at 20 degrees Celsius at 1 atmosphere of pressure under a piston, and then I'm going to push down in that piston until the volume is half of what I started with. And at the same time, I'm applying heat to this. I'm raising the temperature just to see what the heck happens. So I want to know what the pressure of the gas is under that piston. So once again, the key is tabulating the data. I'm starting out at 1 atmosphere, 1 liter, and my temperature is 293 Kelvin. I don't know what the final pressure is, but I know that I've decreased the volume to 0.5 liters, and the temperature is now balmy 50 degrees Celsius, and that would correspond to 323 Kelvin. So there's my equation, and I'm just going to make sure I sort all of those numbers I tabulated into the right spots. And when I do that, it looks like this. I want to get P2 all by itself. So I'm going to need to multiply both sides by 323 Kelvin and then divide both sides by 0.5 liters in order to get P2 all by itself. So I basically did this all at once here. So you can see that the units and numbers will cancel out on the right-hand side, and then they'll hang out on the left-hand side, and the units will cancel. I've got kelvins in the top and the bottom, liters in the top and the bottom on the left side. So the only units that are going to survive on the left side are atmospheres. So I simplify it down a little bit and then do the calculation. I got 2.2 atmospheres, and I was expecting the pressure to go up because I know when I push down on the piston, the pressure goes up. I know also that when the temperature goes up, it's going to increase the pressure, so it doesn't surprise me that I more than doubled the